Good morning, students. So today's class we are going to study about the design of FIR filters using Windows. So here, the last class we have studied about the design of FIR filters. Now we are going to use windowing technique. So here, initially the desired frequency response of the filter is given by H3 of e power j omega equal to summation n equal to minus infinity to infinity H3 of n e power minus j omega n. In that you have to apply the inverse Fourier transform. If you apply the inverse Fourier transform, it is H3 of n equal to 1 by 2 pi integral minus pi to pi h of e power j omega into e power j omega n d omega. So you will be getting H3 of n. But the H3 of n is having infinite length. So we have to truncate it. So if you want to truncate it, we have to multiply the using window. So if you are not doing the truncation, so in that case, it will create the Gibbs phenomenon, some undesired oscillations in the pass band and stop band, so which is called as Gibbs phenomenon. To reduce this undesired oscillation in the pass band and stop bands, we are going for multiplying the filter coefficients with the window coefficients. So if you see after multiplying the windowing sequence, the sequence will be becomes infinite sequence becomes finite sequence. So if you see h of n equal to h3 of n into omega w of n for all modulus of n less than or equal to n minus 1 by 2, 0 for modulus of n greater than n minus 1 by 2. So this is the frequency response of H of e power j omega. In terms of frequency response, you can see that H of e power j omega, it is multiplied by the windowing function. So now if you see, this is the window function, H of e power j omega. This is the rectangular window and its corresponding H of n. Inverse Fourier transform is applied to obtain the H of n, which is given in domain here in terms of discrete. And this is the rectangular window function W of n, it is given like this. When you multiply these two, you will be getting that expression like waveform like this. So this is the waveform which is obtained after applying the windowing technique. The rectangular window, it is defined as WR of n equal to 1 for n varies between minus n minus 1 by 2 to n minus 1 by 2, 0 otherwise. So this is the rectangular window in which when you consider capital N equal to 25, it means 25 number of samples. So n minus 1 by 2 means 25 minus 1, 24 divided by 2, 12. So what will happen? It is minus 12 to plus 12. The amplitude is 1. Next for Hamming window, it is defined as WHN of n equal to 0.5 plus 0.5 into cos of 2 pi n divided by n minus 1, where small n varies between minus n minus 1 by 2 to plus n minus 1 by 2. If you substitute the capital N value as 25, it will be minus 12 to 12. That's why the response is drawn with minus 12 to 12. This is for Hamming window sequence. Then for Hamming window, it is defined as WH of n equal to 0.54 plus 0.46 cos of 2 pi n by n minus 1 for n varies between minus n minus 1 by 2 to plus n minus 1 by 2. If you substitute the n value as 25 here, then the limit is minus 12 to plus 12. So that is what the Hamming window sequence is drawn here from minus 12 to plus 12. Then for Blackman window, the formula is WB of n equal to 0.42 plus 0.5 cos of 2 pi n by n minus 1 plus 0.08 cos of 4 pi n by n minus 1 for minus of n minus 1 by 2 less than or equal to n less than or equal to n minus 1 by 2, 0 otherwise. So in this, we have to substitute the n value, capital N value as 25. So it becomes minus 12 to 12. So for minus 12 to 12, this is the response which is obtained for Blackman window. Thank you.